Hello guys, in this video I'm going to show you how to solve any kernel map or any kernel map, okay, in a very easy way. So we're going to use a calculator, online calculator, in which you input like the truth table, and this calculator will give you the final equations and even draw for you or sketch for you the kernel map with the simplifications done in there. Okay, you might do kernel map like for small like problems, maybe 3 inputs, 2 inputs, but when you have like 4 inputs and multiple outputs, like 8 outputs or 7 outputs, like a 7 segment display, for example, or maybe 5 inputs, you're gonna have like very big kernel maps with very basically very difficult to solve by yourself. Okay, without you can solve, but you might have some errors. Okay, so fortunately there are like some online calculators that can do that for you, called Logisim. Okay, I knew this calculator from a video that I watched, and I'm gonna also leave the video for you. It's very good video. But this video talks about other stuff as well, so I'm gonna just concentrate on the Logisim, and very credit to him to show us this way. Okay, so how to basically use Logisim? First you want to install it. So as you see in the screen here, this is Logisim. Okay, I'm gonna leave this link in the description. You can also search for it, Logisim, and it's the main website will appear for you, and the link for that website here will also be available out there. Okay, then you can download. Okay, and install, of course. But to install it, you need to have like Java version 8 or maybe higher. So you need also to install Java. It's very simple, like 10 second, and I'm gonna also leave this link in the description as well. Okay, so I already did that. I installed basically Logisim. So let's see how to use it. So we have Mr. Logisim here, and okay, and we have also a problem, to do. So let's basically do a very simple problem first. Okay, I'm gonna do like an AND gate. Of course, we know the AND gate is very easy, but let's do it, together. So after opening Logisim, okay, you can find it here, just like Logisim, and it should appear to you. Just open it. So go to project menu here, project tab, and analyze circuit. Okay, I'm gonna do very simple, like 3 input AND gate, very easy. So let's assume the inputs is A, B, C, and it doesn't have to be like capital letters, but I just to differentiate between input and output, we're gonna do the inputs as capital, the output as small letters. Okay, output, just one output for the AND gate. Let's call it Y or whatever, Y. Okay, add, and then you enter the truth table. Okay, and the AND gate is very easy. Everything is 0 except the last case, which in all the inputs are ones, is 1. So this is 0. Just a click, or you can click, or if you go with arrows, you can convert this don't care. This is not X, by the way. This is a don't care. In a kernel map, you can input 0, 1, or don't cares. Okay. In this example, we don't have don't cares, but the next example that we're gonna do, which is more complex, which is 7 segment display, it's gonna have many don't cares. So everything is 0 except the last case will be 1. Okay, then you click build circuit. You can call it whatever, like call it AND gate, for example. And also you can get the output using only 2 input gates, or base is a circuit, or only NAND gates. In some lesson we're gonna learn is that we can implement any logic gate using NAND gate or NOR gate. So we don't need any of that. So just okay here. Okay, and here is the circuit, an AND gate as we expected with 3 inputs. Okay, what is the expression? As we, assumed, y equal to ABC, A and B and C. We can even see the kernel map. Okay, so the kernel map, of course, this is a 3 input logic gate, so we have 8 squares in the kernel map. So, or the kernel map is 2 by 4, you can say. It has only one, which is that guy here, and this one is basically A, and the one here means BC. Okay, very simple. Okay, let's have another example, more complicated one. So in this example, we're gonna explore the 7-segment display. The 7-segment display has four inputs, because it's a for one segment 7-segment display. It can show the digits from 0 to 9. The highest number here, the largest number is 9. 9 is 1001, which is 4 bits. So this circuit has 4 inputs. Good. But how many outputs you have? You have 7 outputs, because it's a 7-segment, right? So there are 7 segments there. Each segment is an output. Okay. So you have 7 outputs. So for each one of these outputs, it will gonna turn on or off at a certain in a certain case. Okay, based on basically the number you in the input. So for example, in 8, in case like if the input is 8, which is 0 1 0 0, in that case all of them will turn on. In some other cases, like 1, only 2 on the side here will be on, and the others will be off. So each one of these outputs has its own circuit that dependent somehow on the input. Okay, so you have to do the kernel map how many times? 7 times. And this kernel map will be with 16 squares, so it will be a 4 by 4 like matrix. Okay, so it's very tedious, and of course error prone as well. Okay, so we're gonna open a website and this website has already solved the kernel or the kernel map for us. This one here. So in this site here, you have the kernel map, and also so here is the 7-segment. It had 7 inputs. Of course, the ground is we don't care about it, so it will be just connected to 0 all the time. So these are the inputs that we have, and here is 7 segments. I'm sorry, this is a 7-segment itself. So the 7-segment itself, has 7 segment, and each segment is controlled using one of these lines or bins. Okay, these bins will be controlled using 4 inputs. A circuit that has 4 inputs. Okay, and here are all the cases. So if we name these 7 segment with small letters like this, A, B, C, D, E, F, G. Okay, each according to the digit, you're gonna have some of them on, some of them are off. Like in this case here, this is number 1. B, C are on, the others are off. The others are off means 0. And these B and C are on means B is equal to 1, C is equal to 1. This is another example too. Everything is on here except F and C will have 0s, the others have 1s, and so on. Okay. And here is a design. You're gonna see it now. So this is basically the truth table. You have here the truth table. It's truncated. I'm gonna explain why. Because this is a 0 case, a minimum number, minimum digit that should show in the output, and the highest is 9, 1 0 0 1. Okay. So what will be the other cases as we learned in our lessons in digital design about kernel map? When you have unrepresented like case, we just put don't cares. Okay, so I'm gonna see how to do this now. Okay, and for each output, you're gonna have, like, for example, for the A output here, you're gonna forget about this part, just take this part here. 4 inputs with 10 cases and 1 output. Then you're gonna draw the kernel maps. Okay, remember in the case of 1 0 1 0 and so on until 1 1 1 1, you have don't cares. Okay, So these don't cares, can be considered 1 or 0 or just left without any touching according to the simplifications that you want. So for example, for this green rectangle here, because if we take only these 4 ones, it's gonna have an extra input. But if we have like this big green rectangle, you're gonna reduce the inputs, okay, by 1. Okay. So you gonna have do this 7 times, as we mentioned, and this will be the circuit at the end. So how we can do this? Very simply using like Logisim in like 1 minute. Okay, so let's see. Again, we're gonna go to project and analyze circuit inputs. We have 4 inputs. So let's add another one. So we have ABC. Let's call them ABCD. Okay, yeah, ABCD. So we're gonna have another one here, add. And for the outputs, let's remove this and enter them ABCD until G. So A, B, C, D. You can press enter, by the way. A, B, C, D, E, F, G. When you press enter, already add is highlighted, so it's like clicking add. Good. So you have now the outputs. Let's see now the truth. Look at the truth table. This is a complete. So the one on the right here is just truncated, right? So for that truth table here, we're gonna use only the first 10 cases from 0 to 9. 0 to 9 is 10, So, and all these left cases will be from here, I'm sorry, will be only don't cares. Okay. So I'm gonna do something here, not to make any mistake. Yes, I'm gonna reduce the size until just the case that we want and just enter these here. Okay. So we need here 1, not 0. So everything is 1 except the last input G, I'm sorry, output G is 0. Then 0, 1, 1, and everything is 0 again. Then 1, 1, 0, 1, 1, 0, 1. Then 4 ones, 1, 1, 1, 1, 0, 0, 1. Then okay, what we have here? We have this case in here, which is okay, 0, 1, 1, 0, 0, 1, 1. Then the next case is 1, 0, 1, 1, 0, 1, 1. Then the following case is 1, 0, and everything is 1. The next case is 1, 1, 1, 0, 0, 0, 0. Then everything is 1 in here. Then 1, 1, 1, 1, 0, 1, 1. Okay? And just leave the others that don't care. So this is a complete truth table now. Okay? So let's just check here. We have 1, 0, 1, 1, 0, and everything is 1. That's correct. We have everything is 1, then 0, 0, 3 ones, 1, 1, 0, 1, 3. Okay, everything is 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. Then 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. And 1, 3 zeros, 3 ones, 0, 1, 1. And G is also correct. Okay, correct. Okay, let's now, this is the truth table, and without any further like tedious work, just build the circuit. We can call it, for example, 7 segment 2, because I did this already, so I don't want to mess with my previous project. Okay, let's check the expressions for A. Well, let's even see the minimization itself. So this is the output A here. So it's equal to A plus BD. So we have this already. We plus C, that's correct, plus B bar, D bar. Okay, that's correct. So the order, of course, is different, but same expression. So let's take B. So we have B bar, C bar, D bar, C, D. That's correct. Let's take C now. C bar, B, and D. That's also correct. Let's go to D. A. We have B bar, D bar in both. B bar, D bar, B bar, D bar. B bar, C, C, D bar, and B, C bar, D, B, C bar, D. That's correct. Let's take E now. That's easy. B bar, D bar, and C, D bar. That's correct. And this was E, so F now. A, B, D bar, B, C bar, C bar, D bar. That's correct. In G, I know there will be a difference. I'm going to explain now. Okay, for G, this is good. So we have A, that's correct. We have B, D bar. Oh, we don't have B, D bar here. Okay, what we have? We have B, C bar, or B, yeah, B, C bar, B, C bar here, and B, C bar here. And we have B bar, C, B bar, C. So there is a difference now. So the expression here has B, D bar, which is not here, obviously. And we have here C, D bar, which is not here, obviously. Why? By the way, both are 100% correct, but this is very good to mention. So because you can do the simplification in two equal way, but with a resultant with different result. Okay, so let's take a look at the simplifications that is done here and here. Okay, so this blue rectangle is basically this purple or pink, whatever, magenta. This big one here. Okay. Now for the yellow, this yellow rectangle, you know that Carnot map is like continuous. It's like a circle. They are connected. So we can take these two ones with these two x's, considering them as ones. So this is basically this orange rectangle with this orange rectangle. Now, this red square, basically, it's a green here. Okay, what's the difference? The difference is this green rectangle, and it can be done in two ways. This green rectangle and these two purple like rectangles. They are equivalent, but they will result in different expressions. So let's see. What's behind this big green rectangle? We have these two ones. The first one, which is here, is already taken in that yellow box. So we're gonna left with this one. So we need to minimize. To minimize, you try to maximize the number of ones you take in a rectangle or a square. So we have two options. The first option is to consider these two x's as ones, and then draw this green rectangle about it, and this will result in basically C, D bar. Okay, you have another option. You know that the Carnot map is continuous, they are connected, so that edge is connected to that edge. It's like that, and that edge is also connected to that edge. It's like that. So you can consider this x as one and this x as one, then take a square like this, similar to this yellow boxes, one like that and one like that. So take these two with these two. This is what happened with the magenta color here. Okay, and in that case, basically what you end up with for in the row case, we have a change in A, but B is the same, so B, and that here we have 0, and we have here 1, 0, 0, so BD bar. Okay, BD bar, which is the expression in here. Okay, that's why they are equivalent to each other. Okay, but remember, with this video was about Logisim, this tool, this magic tool, actually, that will save you a lot of time doing these Carnot maps yourself. Okay, you can still do yourself, but please use the Logisim to basically verify that your answer is correct. Okay, or even determine if you have some mistake and try to correct it. So you're gonna perfect more doing Carnot maps. Okay, guys, thank you very much for watching and have a nice day. Bye-bye.